Hello everyone, myself Soumya BG, Assistant Professor, Department of ECE, SJBIT. In this session, I'll be discussing about the Module 1 topic of microwave and antennas. The Module 1 is about microwave sources and transmission lines. Let us first discuss about the first topic, Gunn diodes. The microwave solid state devices. The special electronics effects encountered at microwave frequencies. They actually limit the usefulness of transistors in most circuit applications. And using these vacuum tubes for low power applications becomes impractical. Hence, there is a need for small sized microwave devices, and this has caused extensive research in this area. Due to this research, the solid state devices are being produced which can be used in higher and higher frequency ranges. The new solid state microwave devices, they are predominantly active. They are two terminal diodes, and the examples may be tunnel diodes, varactors, transferred electron devices or Gunn diodes, and avalanche transit time diodes. In this session, we are actually discussing about the Gunn diodes. The Gunn diodes belongs to the category of microwave solid state devices. Why these devices are actually produced is the special electronics effects which are encountered at microwave frequencies. They actually limit the usefulness of transistors in most circuit applications. And for these low power applications, if we use the vacuum tubes, it becomes impractical. Therefore, a need for small-sized microwave devices has caused extensive research in this area, and this research has produced solid-state devices with higher and higher frequency ranges. The new solid-state microwave devices, they are predominantly active. They are two-terminal diodes, and the examples may be tunnel diodes, varactors, transferred electron devices, or Gunn diodes, and avalanche transit time diodes. This slide gives a diagrammatical representation of the Gunn diodes, practically how the Gunn diodes look like. This is how the Gunn diode will be. Here, as you can see, these pictures actually show the terminals of the Gunn diodes. The Gunn diodes are transferred electron devices. They are widely used in microwave RF applications, and they are mainly used in the frequency range of 1 and 100 gigahertz. The microwave solid state device example. One of the example is Gunn diode. That is the topic of discussion now. The Gunn diodes has one more name called transferred electron devices, TED. They are mainly used in microwave radio frequency applications in the frequency range of 1 and 100 gigahertz. The Gunn diodes may be made up of gallium arsenide, or it may be made up of gallium nitride. When the Gunn diode is made up of gallium arsenide, it is used for frequencies up to 200 gigahertz. And when it is made up of gallium nitride, it is used up to the frequency 3 terahertz. The Gunn diode is most commonly used for generating the microwave radio frequency signals, and these circuits can also be called as transferred electron oscillator or TEO. Apart from generating the microwave signals, these Gunn diodes can also be used as amplifier, and in such a case we call them as transferred electron amplifier or TEA. Transferred electron amplifier or TEA. The Gunn diodes, coming to the advantages of Gunn diode, they are very easy to use. They form a relatively low cost method for generating the microwave RF signals. This is the most important advantage of the Gunn diode. They are easy to use. They form a relatively low cost method for generating the microwave RF signals. So, basically the Gunn diodes are transferred electron devices. They are used in microwave RF applications for frequencies from 100 to 100 gigahertz. They are mainly made up of gallium arsenide or gallium nitride. When it is made up of gallium arsenide, it is used for frequencies up to 200 gigahertz. When it is made up of gallium nitride, it is used up to the frequency 3 terahertz. And these Gunn diodes are mainly used for generating the microwave RF signals, or they can be used as an amplifier. When it is used as oscillator, it is called as TEO. When it is used as amplifier, it is called as TEA. The Gunn diodes are very easy to use. They form a relatively low cost method for generating the microwave RF signals. Now let us discuss about the construction part of this Gunn diode. The Gunn diode usually consists of only of n-doped semiconductor material. The p-doped semiconductor material is not present in the Gunn diode. It is consist of only n-doped semiconductor material. Whereas when we talk about normal p-n junction diodes or any other diodes, they consist of both p and n-doped regions. And in practice, a Gunn diode has a region of negative differential resistance. The Gunn diode, it is having a region of negative differential resistance. This is very important. And this Gunn diode is a unique component. Even though it is called as a diode, it doesn't contain a p-n diode junction. It is called as a diode. But when we call it as diode, usually when we call the element as a diode is when it is having a p-n junction. But here there is no p-n junction because it consists of only n-doped semiconductor material. Why it is called as diode is because it is having two electrodes similar to the p-n diode. The Gunn diode or the transfer electron device can be termed as a diode because it does have two electrodes. And the Gunn diode operation basically depends on the fact that it has a voltage controlled negative resistance. The Gunn diode operation basically depends on the fact that it has a voltage controlled negative resistance. The negative resistance is controlled by the voltage. These Gunn diodes are actually named after the person by named J.B. Gunn, who invented these Gunn diodes in 1963. He discovered a periodic fluctuations of current which pass through then type gallium arsenide specimen when the applied voltage exceeded a certain critical value. What actually he found out during that time in 1963 is that in the gallium arsenide specimen, when some voltage is been applied, he saw some periodic fluctuations of the current, and those periodic fluctuations of the current, they occurred when that applied voltage exceeded a certain critical value, and this is called as Gunn effect. Due to this, there exists a region of negative resistance resulting in this generation of the signal. Now let us discuss what is actually the Gunn diode, Gunn effect. Now in this slide, as you can see, a schematic diagram of uniform n-type gallium arsenide diode with ohmic contacts at the end surfaces are being shown. This is a n-type gallium arsenide diode. N-type gallium arsenide diode. There are two electrodes here. One is cathode, another one is named as anode. And here there is a metal coated contact through which the cathode is being taken. Similarly, here also there will be metal coated contact through which the anode is being taken. And as you can see here this is the length as well as the breadth area, that is 75 micrometer is a length and breadth is 100 micrometer. And the J.B. Gunn, he observed the Gunn effect in this n-type gallium arsenide bulk diode in 1963. Now let us understand how actually devised the Gunn effect. We got to know that above some critical voltage corresponding to electric field of 2000 to 4000 volts per centimeter, the current in every specimen, it became a fluctuating function of time. Above, I got to know that about some critical voltage corresponding to some electric field of 2000 to 4000 volts per centimeter, the current, it became a fluctuating function of time. And in this gallium arsenide specimen, this fluctuation, it took the form of a periodic oscillation which is superimposed upon the pulse current. And in this gallium arsenide specimen, this fluctuation actually it took the form of a periodic oscillation which is been superimposed upon the pulse current. And the frequency of oscillation was actually determined mainly by the specimen in the gallium arsenide specimen, and it was not determined by the external circuit. And this period of oscillation was inversely proportional to the specimen length, and it was closely equal to the transit time of the electrons between the electrodes. And this transit time was actually calculated from their estimated velocity of slightly over 107 centimeter per second. And the peak pulse microwave power which was actually delivered by this gallium arsenide specimen to a matched load was also measured. And they got to know that value as high as 0.5 watt and 0.15 watt were found, and it was corresponding to 1 to 2% of the pulse input power. It was corresponding to 1 to 2% of the pulse input power. Let me repeat the analysis again. A Boson critical voltage which was corresponding to the electric field of 2000 to 4000 volts per centimeter. The current in every specimen it became a fluctuating function of time. And in the gallium arsenide specimen, this fluctuation took the form of a periodic oscillation which was superimposed upon the pulse current. The frequency of oscillation was determined mainly by the specimen and not by the external circuit. The period of oscillation was usually inversely proportional to the specimen length and closely equal to the transit time of electrons between the electrodes. This was actually calculated from their estimated velocity of slightly over 107 centimeter per second. The peak pulse microwave power which was delivered by the gallium arsenide specimen to the matched load was also measured. Value as high as 0.5 watt and 0.15 watt were found, which was corresponding to 1 to 2% of the pulse input power. From this analysis, the Gunn observed that the carrier drift velocity is linearly increased from 0 to a maximum when the electric field is varied from 0 to a threshold value. And this was actually shown through this waveform. Here in this, the electric field is being taken on the x-axis, which is in kilovolt per centimeter. The drift velocity is taken on the y-axis, which is centimeter per second. This carrier velocity, it increases linearly from 0 to the maximum as this electric field is being varied from to the 0 to the some threshold value. And once this threshold is being reached, as you can see here, there is a periodic fluctuations of the current which occur and they are actually the function of time. Now in this, as we can see, when the electric field is beyond the threshold value of 3000 volts per centimeter, here this is 3000, 1, 2, 3, this is 3000 volts per centimeter. For this n-type gallium arsenide, the drift velocity it decreases and the diode exhibits negative resistance. When the electric field is beyond the threshold value of 3000 volts per centimeter, for this n-type gallium arsenide, the drift velocity is decreased and the diode exhibits the negative resistance. Okay, and this diagram actually shows the current waveform of a n-type gallium arsenide, and this actually shows the current fluctuations. The current waveform was produced by applying a voltage pulse of 16 volts amplitude. Here the current waveform, whatever been produced here, it was actually produced by applying a voltage pulse of 16 volts amplitude. The voltage pulse amplitude is 16 volts and 10 nanosecond duration. The duration is 10 nanosecond. This was actually applied to the specimen of n-type gallium arsenide, which is having 2.5 to 10 power minus 3 centimeter in length. And accordingly, the oscillation frequency was 4.5 gigahertz, and the lower trace has had 2 nanosecond per centimeter in the horizontal axis and 0.23 ampere per centimeter in the vertical axis. And this upper trace was whatever you are seeing here is the expanded view of this lower trace. And Gunn actually found that the period of these oscillations was equal to the transit time of the electrons through the specimen, which was calculated from the threshold current. The period of these oscillations is equal to the transit time of the electrons through the specimen, which is calculated from the threshold current. In this, the current waveform was actually produced by applying a voltage pulse of 16 volts amplitude and 10 nanosecond duration to a specimen of N-type gallium arsenide of size 2.5 × 3 cm in length. The oscillator frequency is 4.5 GHz. The lower traces had 2 nanosecond per centimeter in the horizontal axis and 0.23 ampere per centimeter in the vertical axis. The upper trace was an expanded view of the lower trace, and Gunn found that the period of these oscillations was equal to the transit time of the electrons through this specimen, which is calculated from the threshold current. Gunn also discovered that the threshold electric field ETH, it varied with the length and type of the material. One more thing that Gunn actually discovered was that the threshold electric field ETH, it varied with the length and type of the material, and he developed an elaborative capacitive probe for plotting the electric field distribution within a specimen of N-type gallium arsenide of length L, which is equal to 210 micrometer, and cross-sectional area 3.5 into 10 power of minus 3 centimeter square with a low field resistance of 16 ohms. Gunn actually developed an elaborative capacitive probe for plotting the electric field distribution within a specimen of N-type gallium arsenide of length L is equal to 210 micrometer and cross-sectional area 3.5 into 10 power of minus 3 centimeter square with a low field resistance of 16 ohms. And the current instabilities occurred at a specimen voltages above 59 volt, which means that the threshold field is ETH is equal to V by L, that is equal to specimen voltages above 59 volt. So the voltage is 59 divided by, what is the length here? 210 micrometer. So 210 into 10 power of minus 6 into, since we are taking a centimeter, we need to convert that meter to centimeter again. So that results in 2810 volts per centimeter. So we got to know that the threshold field that has to be varied, that has to be considered here is 2810 volts per centimeter. In order to find this, we got to know this ETH varied with the length and type of the material. So getting the length of the material, the gallium arsenide of length L is equal to 210 micrometer was considered as well. Here the specimen voltages was also noted down. It was about 59 volts. Taking these into consideration, the threshold voltage was calculated and it was equal to 2810 volts per centimeter. This is how the gallium arsenide Gunn slice looks like. As I told, it is made up of only N-type material. So this is the N plus substrate, and this is a active layer, and after this active layer again we have got a contact, a gold halide contact, and then we have got cathode as well as anode. A gold wire has been taken in order to represent the anode, and in the cathode we have got a heat sink also in order to get resistance with respect to more heating. Practically this is how the Gunn diode looks like. As I told just now, in the cathode a heat sink has to be used in order to get resistance with respect to the heating. So there is a heating material here, and the anode and cathode are being represented. Let us conclude the topic of our discussion, that is Gunn diodes. The Gunn diodes are also known as transferred electronic devices or transferred electron devices, TED. And the Gunn diode are basically used for high frequency oscillations, that is they are mainly used in microwave RF applications. This is about the principle of operation of the Gunn diode, that is Gunn effect, and the construction of the Gunn diode, and why actually we use the Gunn diode, what are its advantages. Thank you.